One question, two views. You decide.
So yeah, that's the big question, right? How did they get these massive blocks, 147 meters, that's almost 500 feet, straight up into the air? And this is where the experts really split into two different camps. The first camp argues that, hey, the ancient Egyptians were just brilliant engineers who figured it all out with what they had, ramps, sledges, and a whole lot of manpower. But the second camp? They look at the sheer physics of the problem and say, no way, those tools just don't cut it at this scale. They believe a key piece of Egyptian technology is completely missing from the history books. To really get a handle on this, we're going to look at the three core arguments where these two views clash head-on.
So, was it just brute force combined with some seriously clever engineering? Or is there a missing piece to the puzzle? Let's dive into the first major hurdle everyone has to deal with, the ramp itself.
All right, argument number one, the physics of ramps. This is where we get into the nitty-gritty of gradient, friction, and the absolute limits of human strength. It all comes down to how steep you can possibly make a ramp before the whole system just bails.
And this is where things get really heated. The whole debate kind of boils down to this one question. Just how steep was that ramp? One side argues for a pretty steep, efficient ramp that was totally doable. But the other side claims a ramp that steep would have been incredibly dangerous, maybe even catastrophically unstable for the poor guys having to pull the blocks.
Let's talk about this number, 16.4%. The known methods view really hangs its hat on this specific gradient. And listen, they didn't just pull this number out of thin air. It's based on real archaeological evidence from other places, like the Hatnub Quarry, where we know they use steep ramps. The thinking is, if you can just get a handle on the friction, this steep angle is the perfect sweet spot. It gets the job done without needing a ramp so long it would stretch for miles and miles.
Okay, so how do you actually manage the physics on a slope that steep? Well, View 1 says this was basically a solved problem. By pouring just the right amount of water on the sand in front of the sled, you lubricate the path, and that brings the force needed to pull a 2-ton block down to something a team of about 20 guys could totally handle. But this is exactly where View 2 jumps in and says, hold on a minute. To make the path slippery enough for the sled, you're also making it dangerously slick for the workers trying to get a foothold. They argue you just can't have it both ways. You can't have low friction and safe footing. Something's got to give. So the missing capability camp draws a hard line in the sand. They propose a much, much lower limit, a maximum safe gradient of just 8%. They argue that anything steeper than that becomes biomechanically unsafe, and you risk the teams losing control of these massive stones. But, and this is a huge but, a ramp with a gentle slope of only 8% would have to be miles long to reach the top of the pyramid. And for a structure that massive, there is zero archaeological evidence, nothing.
Okay, let's move on to our second big point of contention, ramp geometry and throughput. Look, even if you solve the steepness problem, you slam right into another massive challenge. This isn't just about lifting one block. It's about maintaining a constant, steady flow of millions of blocks. It's a logistics nightmare, especially when the pyramid gets really narrow near the top.
The known methods view offers a really clever two-part solution to this traffic problem. First, you build a massive 2-lane main ramp, like a highway, that handles the vast majority of the pyramid's volume, about 86% of it, up to 71 meters high. Then, as the pyramid gets smaller, you switch gears. You move to a narrower single-lane helical ramp that spirals around the outside. For this part, you use smaller blocks and smaller teams. It's a totally adaptive system, designed to change as the pyramid itself changes shape.
So, does it work? View 1 says absolutely. Their phased system lets them keep up an incredible delivery rate of about 23 blocks an hour. But View 2 looks at that plan and sees a giant geometric trap. A helical ramp means you have to make tight 90-degree turns. Imagine trying to move a giant sofa around a sharp corner in a narrow hallway. Now do it with a 2-ton stone block. They argue these corners would create unavoidable traffic jams, causing the whole delivery system to just collapse. That theoretical rate of 12 blocks an hour on the upper levels, it would probably plummet to just 3 or 4 in the real world.
And this is where the missing capability side lands a pretty big punch. They point to a major flaw in the helical ramp model, and it's something even the people who support the theory admit. The ramp literally reaches a dead end about 5 meters short of the top. It just runs out of room. So think about what that means. Even if this ramp system was real, they still needed another totally unknown method to get the final stones into place, which kind of proves the point that a piece of the puzzle is missing, right?
The argument even comes down to just looking at the pyramid today. View 1 says, look, the tapering shape of the pyramid perfectly matches our tapering ramp system. It's a rational design. But View 2 says, go look closer at the actual stone layers. They don't look uniform at all. Instead, you can see about 15 distinct bands where the block sizes suddenly change. They argue this is physical evidence written in stone that argues against a single continuous ramp system. It suggests they were using different lifting methods at different heights.
All right, on to our third and final argument. And honestly, this might be the biggest challenge of all. We're talking about lifting the absolute heaviest stones in the entire pyramid. This is where the physics and the logistics get pushed to their absolute breaking point. We're talking about the massive granite beams, some weighing as much as a space shuttle, that had to be lifted to the very heart of the structure.
I want you to just pause on that number for a second. 75 tons. That's 150,000 pounds. These are not your standard limestone blocks. These are monolithic granite beams that make up the roof of the king's chamber, way up inside the pyramid, nearly 60 meters off the ground. Any theory that wants to be taken seriously has to explain how they pulled this off.
So how in the world do you move something that heavy? View 1 says you just scale everything up. Look, we have ancient depictions of 172 men moving a 60-ton statue. So it stands to reason that an 800-person team could pull a 75-ton beam up their 16.4% ramp. It's just a matter of adding more muscle. But View 2 looks at that and just says, that's a logistical fantasy. Have you ever tried to coordinate 800 people to do anything at the same time? It would be pure chaos. The slightest imbalance would cause ropes to go slack, control would be lost, and you'd have a 75-ton catastrophe on your hands.
And let's say you somehow do get the beam up to the right level, the job's not over. You still have to get it into its final resting place. View 1 suggests they could have used known simple machines, like levers, or maybe shear legs, which are kind of like an A-frame crane. But for View 2, this is the final breaking point. Shear legs need a perfectly stable, level platform to work from, and that just doesn't exist on the sloped, messy surface of a half-built pyramid. Plus, they argue you can't just take an experiment that lifts 1 ton and assume it'll work for 75. The physics just doesn't scale up that neatly.
So for View 2, these 75-ton beams are the ultimate impasse. It's the point where the whole conventional theory falls apart. The massive teams can't be coordinated, the simple cranes are impractical, the science doesn't scale up, and by the way, there's no evidence for the gigantic timbers you would have needed anyway. For them, this is the smoking gun. It's the moment where Old Kingdom tools hit their absolute mechanical limit, proving that some other more advanced technology had to be involved.
So there you have it. We've broken down the 3 core battlegrounds in this debate: the physics of the ramp, the logistics of actually moving all those blocks, and the ultimate test, lifting those 75-ton granite beams.
And it all brings us right back to that one fundamental question. Was this a story of incredible human ingenuity, pushing ancient tools right to their absolute limits? Or was there something else going on entirely?
We've seen it on every single point, from the angle of the ramp to the traffic flow, to the placement of those final massive beams. For the exact same evidence, we have 2 completely different interpretations. We've laid out both sides of the argument, and as always, we're not here to take a position. It's pretty clear that in the end, this whole debate really comes down to a fundamental question about limits.
So what's your take? Do you see a triumph of conventional engineering, a masterpiece of planning and human power? Or do you see a point where the evidence seems to defy the known rules of physics and logistics, hinting at a lost technology that remains one of history's greatest unsolved mysteries?
We really want to know what you think. Which argument or piece of evidence do you find the most compelling? Jump into the comments and share your view. And hey, if there's another historical puzzle you want us to tackle next, let us know below.